Today we will solve the problem of constructing a binary search tree BST from pre-order traversal. So this is the problem statement which we'll be solving today. So let's first understand what is a BST. BST is a binary tree in which every node, every left child, we can say, every left child is less than the root and every right child is greater than the root. So this holds true for all the nodes, all the internal nodes of a binary search tree. For the root nodes, anyhow, the childrens are null, right? The children are null for the root node, so it doesn't make sense. But for every root node, for every internal node, left child will be less than the internal node value, and right child will be greater than the internal node value. So this is the property of binary search tree. And what is pre-order traversal? In pre-order traversal, we first visit the node, then the left subtree, and then the right subtree. So this is what we do in pre-order traversal. We can also call it as VLR, say, or NLR, node left right. So this is the meaning of pre-order traversal. Now let's do one simple pre-order traversal to understand what a pre-order traversal is. So suppose this is 15, this is say 10, this is 20, and this is 5, 4, this is 1, and let's say make it 2, let's make it 3, and let's make it 1. Yeah. So this is one binary search tree. And what would be the pre-order traversal for this? Let's see. We have to visit the node first. We'll start from the root. We'll visit the node 5. We'll go to the left subtree. We'll visit the node 4. Similarly, we'll visit 2. We'll visit 1. Then we'll come back, backtrack. We'll visit the right child of 2. So we'll visit 3 now. Then nothing is there. It's a leaf node. So again, we'll backtrack. We'll go to 4. 4 doesn't have a right child. So nothing can be done here. No nodes to visit here. Again, we'll backtrack. 5 is already visited. We have visited the left subtree of 5 completely. Now we'll move to the right subtree. Okay. So we'll first visit the node 15. Then we'll go to the left, right? We'll go to the left. So we'll visit 10. Then it's a leaf node, nothing to be visited further. We'll backtrack. We'll go to the right child of 15. We'll visit 20. So this is the pre-order traversal of this BST, this binary search tree. Why this is a binary search tree? Because every node, every left child is smaller than the root node or its parent node basically. Every left child is smaller than the parent, its parent node. 4 is less than 5, 2 is less than 4, 1 is less than 2, right? 10 is less than 15. And every right child is greater than its parent. So 20 is greater than 15, 3 is greater than 2, right? 15 is greater than 5. So that's why this is a BST, binary search tree. Now let's see if we are given this pre-order traversal in a vector form, how can we construct a binary tree, binary search tree? Let's see that. So there are a couple of ways to do that. To do this, we know that if we have a pre-order traversal, if we know pre-order traversal and in-order traversal of a binary tree, then using these two, we can construct a binary tree and a binary search tree also for that matter. So if we have pre-order traversal and in-order traversal, definitely we can do that. So if we are given the pre-order traversal, how can we get the in-order traversal of the tree, of the BST? So we know that there is this property of BST that if we do in-order traversal of a BST gives us the nodes of BST in sorted order. Always. Always this property holds true. So if we do in order traversal of a BST, the nodes which will get back as output, that will be in sorted order always. So this is the property of binary search tree. So what we can do here is we can sort this we can sort this, right? We can sort the pre-order traversal given to us and get the in-order traversal vector, right? This is one way. Sort the sort pre-order traversal. So what we'll get? 1, 2, 3, 4, 5, 10, 15, 20. So this is the in-order traversal of the BST. This is the in-order traversal of the BST. Okay. What is in-order traversal basically? You might be knowing that, but just to repeat it. So in order traversal, we visit the left child of a node or the left subtree first, then the node, and then the right subtree. For every node, we first visit the left subtree, then we visit the node, and then we visit the right subtree. So this is the in-order traversal. Right, so we can get the in-order traversal by sorting the pre-order traversal, and we can make use of these two for constructing the binary tree. But what will be the time complexity for this? For sorting, suppose there are n nodes in tree in BST, okay, and that's why we'll have n nodes in the pre-order traversal also. So for wait just a minute, yeah, we have n nodes in the BST. So for sorting this, what will be the time complexity? Order of n log n, right? If we use merge sort or any suitable sort for the array given to us, vector given to us, the time complexity would be order of n log n, right? And then what will be the time complexity for constructing the BST? Time complexity for constructing BST would be order of n using pre-order traversal and pre and in order traversal. So the total time complexity would be order of n log n plus order of n. Sorry, order of n log n plus order of n. Can we minimize it? Can we minimize this time complexity? Is it possible to minimize the time complexity? Let's think about it. There is another approach which we can make use of to construct a BST from its pre-ordered traversal. So just for the reference, let's again copy the 54213 15 10 20 54213 54213 15 10 20. Yeah, this was the pre-order traversal given to us. So what we can do is we can iterate we can iterate through this pre-order traversal vector given to us, okay, and I'll just mention the indices here. Yeah, this is the vector given to us, these are the indices, right, from 0 to 7, and we have to traverse through this vector one by one and create the node for that particular value, for each of these particular values, and decide whether the upcoming element should go in the left subtree or the right subtree of the current node. For example, first we'll encounter this 5, Then we will see whether to insert this 4 in the left subtree or right subtree. So we know that 4 is less than 5, so it will go in the left subtree to to ensure that the BST property is followed. Now we will encounter 2. We'll see that okay, 2 is less than 5, so it will go to left subtree. Then we'll say that 2 is less than 4 also, so it will again go to the left subtree of 4. For 1, what will happen? Again, it's less than 5, less than 4, less than 2, push it here. For 1, what we can see is, okay, it's less than 5, no, 1 is done, sorry. For 3, what we'll do is, it's less than 5, less than 4, but greater than 2, so it will come as the right subtree, right child of 2. We'll go to 15, we'll see that, okay, 15 is greater than 5. So we'll come here, we'll see, now we'll go to 10. We'll compare, okay, 10 is greater than 5. It will come to the right child, then it will compare, okay, 10 is less than 15. So it will go to the join as the left child of 15. Now the next node is 20. The 20 will compare with 5, okay, it's greater than 5. So come here, it's greater than 15. So okay, it will become the right child of 15. So this will take big O of n, order of n time complexity. Why? Because we are traversing the pre-ordered traversal vector given to us, right? We may traverse a few nodes, maybe more than once, but that doesn't really matter. The time complexity will be big O of n only. It may be some constant here. Sorry, yeah, it may be some constant here, but still the time complexity will be big O of n. So this is a better approach. Now, how will we code this? How will we code this? So for this, if we, at every instance, if we have the if we have something called an upper bound with us, then we know whether a node can be inserted or a node can be made the left child of the current node or not. For example, when initially when our tree is empty, I mean there is no node and we've just started the traversal of this pre-order vector, now we'll first encounter 5. So what is the upper bound of the element which we can store? It is int max, right? We can store anything, any number in the tree which is less than int max initially, right? So we will create 5 here. Nothing is there, right? Initially, so that's why upper bound is int max. We'll create 5. Now, as we create 5, what we'll do, we will here, what we'll do, we'll make upper bound equal to 5. Now 4 comes. We'll check if for the left child we will make the for the left subtree the upper bound is 5, right? For the right subtree still the upper bound is int max only. Why? Because here we can insert anything which is greater than 5, correct? Up to int max. But in the left subtree, the upper bound will be 5 only because in the left subtree we can insert elements which are less than 5. So now the next element will come 4. We'll check whether it is less than upper bound or not. Yes, it is less than upper bound, right? It is less than upper bound. So we'll come, we'll make it the left child. And upper bound for the left subtree of 4 will become 4 and upper bound for the right subtree of 4 will become 4 will be 5 only, right? Because anything greater than 4 will come to the right child but it should be less than 5, right? Then only that particular element can come here. Understood, right? So that's why the upper bound will be 5 here, which is basically equal to the previous upper bound. So previous we are copying here. So for left child, we update the upper bound, but for the right child, we just take the previous upper bound. Similar, this is what we did in the case of 5 also. The previous upper bound was int max. So for left child, we made upper bound equal to the current element, but for the right child or the right subtree, the upper bound was equal to the previous upper bound, which is int max only. Now the next node will come, next element will come, 2. We'll check if for the first we'll check for the left subtree. If 2 is less than upper bound 5, true. We'll come down, we'll check if 2 is less than upper bound 4, true. Now this is empty, so we'll just create the node. Similarly for 1, so here upper bound is 2 for the left child, and here upper bound is 4 for the right child. Upper bound is same as the upper bound of previous node, parent node. But for the right child, we update the upper bound to the current node value. So that's why when 1 will be encountered, it will come down, come down, come down. It is less than 2, so it will get inserted here. Now next element is 3. 3 is less than upper bound 5, true, it will come here. 3 is less than upper bound 4, it will come here. 3 is less than upper bound 2, no. False, right? 3 is not less than upper bound 2, so it will come down here on the right side. Is 3 less than upper bound 4? Yes, this is true. So we'll get it inserted here, and so on and so forth for the remaining elements also. So now we'll write the code for this, so you will have a better understanding. So yeah, we have the problem of constructing a binary search tree from pre-order traversal. Let's see if there is any constraint which we need to take care of. So the number of nodes in the pre-order is 1 to 100, and the values are 1 to 1000. So we can use the integer to store the intermediate values. All the values of pre-order are unique, right? Fine. So now what we need to do is first create a index variable int I equal to 0, and initially the upper bound, as we discussed, will be int max, so we will just initialize that as well. Now we will basically take the help of a recursive function helper. We'll just return that, no need to do anything else. Return helper pre-order I and upper bound. Now we will create this helper function which will basically return a, a node, tree node. It will take the pre-order vector, the index, and the upper bound as the parameters. Now, first will be the case when we have to stop the recursion. We have to stop the recursion when if I is equal to pre-order dot order dot size that we have exhausted and basically ran through all the elements of the pre-order vector, then we have to stop the recursion, or pre-order I is greater than upper bound. If pre-order ith element is greater than upper bound value, then we cannot basically go there and create a node. Basically we have to backtrack, right? For example, here we'll compare first if 7 is greater than if 7 is less than 5 or not. If it is not less than 5, we'll backtrack, we'll not go to the left child, we have to come down here. So that's why we'll have this condition: if pre-order I is greater than upper bound, then return null. Otherwise, create a node, name it as root, and just create it with the value pre-order I. Increment the index, then create the left and right child of the root, pass the preorder I. When we are creating left, the upper bound will be the current element only, right? We know that. So upper bound will be root's value, right? And when we are creating the right subtree, the upper bound will be the previous upper bound. So whatever upper bound we got as parameter, same thing will pass here, and then we'll return root. Now let's run this and see if things are fine. This is accepted. Let's submit this. Amazing. So all the test cases have passed, and now we'll discuss the time complexity and space complexity. So the time complexity is big O of n because we are traversing through the pre-order vector, right, which is of size n. And apart from that, we are not doing any computation, so the time complexity will be big O of n, and the space complexity would be we are not using any space auxiliary space, but yeah, the recursion which we are doing, for that we will need some space, right, for storing the recursion stack. So that will can be at max equal to big O of n in cases where the tree is queued. I mean, we have uh, a skewed tree where every node is like, at the right subtree of the parent node, like for example this one or this one. If we have a skewed tree, then the space complexity can in the worst case can be equal to big O of n, right? So yeah, we saw that the space complexity of this solution is big O of n, and the time complexity is also big O of n. So hope you have understood the solution. If you have any doubts, you can comment in the comment section. Thank you for watching this video.